All right, ladies and gentlemen, today's class recording has started. So, in our last unit, we talked about mechanics, and we said that mechanics is our study of motion. And when we are describing the motion of an object, we talked about 4 questions that we want to answer in order to accurately describe that motion. What are the 4 questions that we want to answer? Where is it? What is it doing? What will it be doing? And when? Right? So, we talked about mechanics, we talked about where, we talked about what, we talked about what next, if I can spell what correctly, and then we talked about when. And I think I mentioned to you guys at the time, there is one W question here that's kind of missing. Why? Well, who, I guess, also, right? But why? When we're describing mechanics, when we're introducing the concept of mechanics, we're just describing. We're not explaining. But in this unit, when we start introducing the idea of forces, that's when we start getting into the why part. Why do these things happen? Why does an object accelerate? Why does it speed up? Why does it slow down? Why does it not do anything? We'll start answering all of those questions over the next couple of days. All right? So, over the course of today, I hope that we're going to answer these 3 questions. We're going to talk about what a force is. We're going to talk about what forces do. And then we're going to talk about some of the different types of forces that exist out there in the universe. All right? Good?
Let's do that.
All right. So, with that being said, let me go here. Oh. All right. So first, what is a force? If I asked you this question, what is a force? A lot of you would probably give me a pretty straightforward answer based on experiences that you've had. So, what is a force? A push or a pull on something, right? That's pretty good. Okay? So, a force is a push or a pull on an object.
Did I get that right, or did I get that right?
I don't think you got that right,
Actually,
actually.
I did say push or pull.
But more importantly, than a force being a push or a pull is what forces do. Right? So, forces cause acceleration. Forces cause acceleration. And that means that forces can do 3 things to an object. What's one thing a force can do? Speed it up, slow it down, or change its direction, right? So if one of these 3 things is happening to an object, that means there is a force on it. Okay? Again, going back to our definitions, right? How do we define acceleration? This is explaining acceleration. How do we define it? Change in velocity, right? Acceleration is a change in velocity, right? Delta V, okay? Any change in velocity is acceleration. So anytime the velocity of an object changes, there has to be a force. And that force, that means we can cause an object to speed up, or to slow down, or to change directions. Okay? Good? All right. With that being said, next. Forces are vector quantities. In the last unit, we learned about vector quantities, right? What does a vector quantity do for us? Magnitude and direction, right? In the case of a force, what is the magnitude of the force going to tell us? How much what? How much we're pushing or pulling, right? Or how much we're forcing, right? So the magnitude of the force, the how big part, is how big are we, or how much are we pushing or pulling, right? How big is that force? Or, like we just kind of said, right? How much push or pull is there? That's the magnitude part. But the direction, right, that's pretty straightforward, right? It's just direction. We haven't done this a whole lot up to this point, but there is a way that we can represent vector quantities to help us figure out what's going on in a situation. What can we use to represent a vector quantity, like if we're drawing a picture or something like that? An arrow, right? Arrows are very, very useful for representing vector quantities. They already have a built-in direction, right? If you draw an arrow pointing in a certain direction, that means that's the direction that that arrow is pointing. So we will find that as we go along here, we are going to use arrows to represent forces. A lot of times, there will be more than one force that's acting on an object, and we're going to have to figure out, well, what does that mean then, right? What is this force doing? What is that force doing? That means that on our pictures, a lot of times we will use arrows to represent those forces so we can look at their magnitude and their direction. Generally speaking, we try to draw the length of the arrow to represent its magnitude, right? So if you have one force that's pushing with a force of 8 and another force that's pulling with a force of 4, the force that's 8 should be about twice as long as the force that's 4. All right, good? Okay. When we make these observations about forces, we see that there are a couple different ways that forces can do their thing. All right? And what is the thing that forces do? What do they do? When they push or pull something, what happens to it? Not it moves. The velocity changes. It accelerates, right? It does something different than it was doing before. Okay? So, the first way that forces work, oh, come on. Yikes.
Oh, that's slipping out.
Come on.
Darn it.
Get this way.
There we go.
All right. So, contact forces. Contact forces change the motion of an object by actual physical contact. These are the things that most of you probably would think of as forces. Pushes, pulls, hits, throws, right? All those kind of things that actually require contact in order to change the motion of an object. Okay? Good? But there are times when the velocity of an object can change like this. Ready? Oh, sorry. Oh, friction. Friction is the other, another big contact force, right? No. Not that they don't trust you with it, that's not the demonstration. All right, you ready? Okay. Did that object accelerate when I threw it up in the air, right? Absolutely. What did it do on the way up?
It slowed down.
Slowing down on the way up. What did it do at the top? What does it do at the top? It stops, but even though it stopped, it's changing directions, right? It was going up, it's going to start going down. Even though the object is currently stopped, it is still accelerating. It is changing directions. And then on the way back down, what is it doing? Speeding up, right? But that all happens even though nothing actually touched this object, right? So another way that forces can work are through what we call field forces, where we're changing the motion of an object, but without actually touching it. Say again? Like a force field, which I'll show you in a second. So the one field force that most of you are probably the most familiar with is gravity, right? It's the one we interact with all the time. It causes things to fall to the ground. It causes you to stay on the earth, all those good kind of things. But there are other ways that we can change the motion of an object without actually touching it, right? Magnets. Magnets can cause things to move without actually touching them, right? Electrical charges, like when you take a balloon and you rub it on your hair, assuming you have hair, right? Rub it on your hair, right? Get it all charged up, and then other people, like you can make other people's hair move, or those kind of things, right? Or things like an electric motor or something like that, where there's not actually some physical contact, but we're actually making things move. Okay? Like the magnetic field, right? Speaking of the magnetic field, let's talk about a force field. Okay? Apparently I didn't add this to the outline, and I really wish I would have. But there's a little bit of space on the side over to the left over there, so if you want to jot some notes in that space. Okay? So, a force field. Unlike what you may picture a force field as through a science fiction movie or a novel or something like that, a force field is an area. Okay? It's the area that surrounds an object where it can affect other objects. Why does gravity affect this ball, make it slow down and then speed back up? Because this ball is in the gravitational field of the Earth. There's an area that surrounds the Earth where its gravity can affect other objects. We live in that gravitational field. So Earth's gravity affects us, Earth's gravity affects this ball, etc., etc. But what else? What other big object is also in the Earth's gravitational field? Any other big thing that you know of that Earth's gravity affects? The moon, right? The moon is within Earth's gravitational field because the gravity from Earth is responsible for making the moon move in its orbital path around the Earth, right? The sun. The sun has a way bigger gravitational field than the Earth does, right? The entire solar system exists within the sun's gravitational field. It's an area where an object can affect another object without actually touching it. Okay? So, you kind of said, like, magnets have a magnetic field, right? The Earth has a gravitational field, but the Earth also has a magnetic field. That's how compasses work. Magnetic objects in the magnetic field of another object are affected, right? That's how a compass always points towards the north, because the magnet in the compass is affected by the Earth's magnetic field. Now, non-magnetic things, like this eraser, right, still exist within Earth's magnetic field, but they aren't affected by it because they're not magnetic themselves, right? Is that good? So, one thing we've noticed, though, is that the strength of the magnetic, or the strength of any field, decreases as we move farther from that object. So the field decreases as the distance increases. What kind of relationship are we talking about there? If one is decreasing, and the other one is increasing. Not quadratic, nope. Not linear.
Exponential.
Nope.
The law of conservation of something.
Just start throwing out words, right? Yeah, so.
Cubic. Quartic.
It is in
Monomial.
it is an inverse relationship. Distance goes up, strength of field goes down, right? Inverse relationships are opposite of each other. One goes up as the other one goes down. So field strength decreases as the distance increases. Okay? Good there? All right, here just some pictures of our different types of forces or how they work, right? This guy is applying an actual force to this box. Look at how much force he's applying, right? 4 lines worth of back force. Whoa, that is, you don't mess around. Well, he's got a back brace on. Don't worry, he's good. So Paul, I would have said his name was Ralph.
Ralph?
Mac.
That's a correction.
That's a Paul.
Oh,
That's a good one. That's a good one. Paul.
So, as opposed to Paul, Greg, Mac, or Ralph applying this force to this box directly, here's Antonio, right? So, no, definitely not. So, here, I know this is not going to help because it's just going to get blurry, but, you know, so, I mean,
It's a dude. It's a dude.
so, you know.
By the
Wow. So, I mean, he's cliff diving. And I always tell myself, even though this picture may be a little misleading, Antonio definitely jumps out far enough that he doesn't, like, you know, land on these rocks.
That's so dangerous.
Because I don't want to believe that I'm showing you a picture of some guy that's going to end up dead. And, you know.
Well, he might end up
Or, you know,
starting
and two, you know, if we wanted to, we could figure out how fast he was going when he hit the rocks because we know, like, the acceleration of gravity and stuff like
We
that.
also
So,
figure out
you know.
how
So
he
if he hits the rocks, right? So we could figure out how fast he'd be going, right? We could also figure out how tall the cliff was, you know, all kinds of good things. So
What if he does?
yes. All right. So. Oh. All right. Next, let's measure force. Okay. So measuring force is a little bit more complicated than measuring distance or measuring time or even measuring speed. Okay? When we measure distance, we just measure the length. One step. When we measure time, we just measure this. We measure the time. One step. When we measure speed, we actually have to make 2 measurements, right? What are the 2 measurements we have to take in order to measure the speed? Distance and time, right? So we've got to combine them together, right? So, if we're going to measure force, we actually have to measure 2 things as well. First, what does force do? Accelerate, right? So we got to measure the acceleration, okay? But there's another factor that figures into this, right? If you apply the same force to 2 objects, will they accelerate at the same rate?
If the forces are the same.
It depends is the right answer, right? If they're the same, let's have to go with weight. Let's go with mass, right? So let's go with just the object itself, right? Because friction is another force, so that gets us into we have multiple forces acting on an object. But if we apply the same force to 2 objects, they won't necessarily accelerate at the same rate because we have to take into account the objects themselves. So, force is measured in a unit called a Newton. Okay? Excuse me. If you can't figure out where that name came from, wait until tomorrow and then we'll explain it. Okay? So, we use the the capital letter N to represent newtons.
Wait, is capital like specifically?
Yes.
I was always trying to vote.
No, capital. So, capital. All right. So 1 Newton, like it says here, is the force that's required to cause an acceleration of 1 meter per second squared, or if we want to talk about it, right, 1 meter per second, on a 1 kilogram object. So first, what does an acceleration of 1 meter per second mean?
It changes the velocity.
Not that it moves 1 meter every second.
It changes the velocity by 1 meter every second.
It changes the velocity by 1 meter per second every second. Okay? So, if we take a look at this picture down here, oh, not that picture, this picture.
What is that?
I'll tell you in a second.
I was like,
That's the example.
All right, that is the example. All right, so
I got it right.
here is a hockey puck. Let's say this hockey puck weighs 1 kilogram. In real life, hockey pucks don't weigh 1 kilogram.
discus is
But
air hockey.
discus wouldn't float as nicely on this air hockey table.
Yeah.
All right, so this hockey puck has a mass of 1 kilogram. If we pushed it, we could make it go faster from 0 to 1. If that takes place over a time of 1 second, how much has the velocity changed from this picture to this picture? 1 meter per second. How long did that take? 1 second. So this acceleration here is 1 meter per second per second. But here, the fact that this hockey puck has a mass of 1 kilogram, that means that that would be the amount of force that we would apply in order to make this happen. No. A Newton is the force that it takes you to put an apple and bring it up to your mouth in order to take a bite of it.
Oh, that's
No.
barely anything.
Not very, Newton is not very big. Okay? Now, let's do this, right? So, 1 Newton equals 1 meter per second for every 1 kilogram. Okay? Let's say that this hockey puck was heavier and it wasn't 1 kilogram, it was 2 kilograms. If we pushed it by the same amount, how fast would it be going here? Only half a meter per second, right? Same force, but because this object is heavier, it doesn't go as fast, right? Let's say we kept applying that force. How long would it take us to get to having it go 1 meter per second?
2 seconds.
It would take 2 seconds, right? Twice as long. Twice as much mass takes twice as long if you use the same amount of force, right? There's a lot of mathematical relationships there that we will talk about more tomorrow when we talk about Newton's second law. Okay? It's pretty good. It's a pretty good one. So, it's pretty important. All right. Are we good with this idea of force and how we measure it? Okay. We'll wrap it up there right now. We will I'll pick it up from there tomorrow, talk about some Isaac Newton stuff.